Hello, my name is Yuchen Liu. Today I want to introduce our work about preventing sensitive word recognition using self-supervised learning to preserve user privacy for automatic speech recognition. This is a joint work with Abu Kapadia, Donna Williamson, conducted at Indiana University in Bloomington. Microphones are everywhere. There are an estimated 3.3 billion actively used smartphones around the globe today, and there is a growing market for digital assistants such as Google Home and Amazon Echo. More than 100 million Alexa-enabled digital assistant has been sold to date. This microphone-enabled devices feature an always listening mode to support voice-based command. People can trigger voice commands easily with spoken phrases such as "Hey Alexa," "Okay Google," and Hey Siri for Amazon, Google, and Apple-based devices. Microphones in these devices, however, raise significant privacy concerns. Existing microphone masking techniques mainly use either ultrasonic signal or adversarial noise to jam the embedded microphone so that the mixed speech cannot be recognized. However, there are still drawbacks to these methods. For ultrasonic jamming methods, it helps to create a variable device that generates ultrasonic jamming signals. Although this approach is effective, unfortunately, it requires highly specialized equipment, so it is not yet a feasible approach for most users. The adversarial noise jamming methods can be divided into optimization methods and generative methods. The optimization methods find a desired perturbation by solving a complex iterative optimization problem, which updates the input signal directly using the gradient from the backpropagation process. This technique does have a significant disadvantage that the inference step is computationally expensive. The inference time is very long, which took several minutes for only one input signal. On the other hand, generative methods is much more efficient, but only word level inputs has been studied and tested. So in this paper, we developed an end-to-end approach that generates audience-specific perturbation that obscure a set of words that has been deemed sensitive. In particular, spoken digits, which may in credit cards or social security numbers, has been chosen as the words that ASR system should not be able to recognize. And all other words should be recognized accordingly. For example, suppose the sensitive word list contains all spoken digits from 1 to 9. The speech waveform that contains the utterance "my password is 2697" should be transcribed as "my password is" by the ASR system after our generated perturbation is added to the speech signal. So for better formulate the problem, given an audio signal X, a list of sensitive words W from W1 all the way to WN, an ASR system F, and then the original transcription Y, recognized by F by input X. In our case, we want to generate a small perturbation delta to create the adversarial example by add the delta to the audio signal X. Once supply their mix to the ASR system, the result transcription should recognize all the words original in Y, except those are containing sensitive word list W. In other words, we want to input X plus delta to F to get Y without all words in W. The model structure of proposed approach is shown here, which consists of three main components: the feature extraction, the perturbation generator, and the target ASR system. The time domain signal is first provided to the feature extraction module that extract high-level features. The extracted high-level features are then fed into the generator, which provides a magnitude response for the desired noise perturbation. The magnitude spectrum for adversarial noise is then generated from element-wise addition of the magnitude spectrogram of the audio signal and the perturbation. The adversarial example is provided as the input to the ASR system. Next, I will introduce each part in detail. So for the feature extraction, we use a pre-trained self-supervised learning framework during the feature extraction stage, which we follow the wave-to-back-to approach. So wave-to-back-to consists of an encoder network and a context network. The encoder network has 5 convolutional layers, and it generates a compressed Latin representation for the audio. The context network has 9 convolutional layers, and it combines the Latin representation into a contextualized tensor. We use the contextualized tensor as our SSL feature to the generator. So we also use the traditional STFT spectrogram as our baseline. Recent studies show that the speech representation obtained using SSL perform better than traditional features such as STFT or MFCC on phonetic classification tasks that they significantly improve ASR performance. It is believed that the extractive features contains more content information that will allow the generator to produce noise perturbation that obscure the recognition of the sensitive words, while also not impacting the ability of ASR model to recognize non-sensitive words. So the generator network consists of a UNet-based encoder-decoder structure that further process the 2D feature extracted by the pre-trained wave-to-back model. In our implementation, the encoder contains 8 2D convolutional layers. Each 2D convolutional layer is followed by a batch normalization layer and a leaky ReLU activation function. The Latin representation from the encoder is then fed into an 8-layer decoder. Each layer from the decoder contains a 2D transposed convolutional layer that is followed by a batch normalization and a ReLU activation function. The last decoder layer uses a hyperbolic tangent activation that restricts the magnitude of the perturbation to a lower level. Also, we use the skip convolutional technique to fill the semantic gap between the low-level encoder outputs and the high-level decoder outputs, which increase the learning capability of the generator. We choose 2 different end-to-end ASR models to test the oneness of our proposed approach. The DeepSpeech 2 is a state-of-art RNN-based approach. The second model is the LRT, which is the low-rank transformer, which use a lightweight transformer to significantly reduce the inference time of ASR. Both ASR models are pre-trained by using the library speech dataset and are held frozen during the training, but the gradient is used during the propagation process to upgrade the weights in the generators. For loss, we use the CTC loss to calculate the distance between the current transcript and the desired transcript. We propose 2 novel evaluation metrics for this task. The first is the manipulation rate, which is the ratio of the number of correctly removed sensitive words and the total number of sensitive words in an utterance. A higher manipulation rate indicates more desired words are being filtered. Other words in the utterance, however, may be negatively affected during the perturbation process. Therefore, we propose a second evaluation matrix, preservation rate. The preservation rate indicates how many of the non-sensitive words are correctly recognized, and hence not disturbed by the perturbation. A higher preservation rate is desired, as it indicates that non-sensitive words are correctly recognized by the ASR system. We used the library speech groups as the data source. Spoken digits from 1 to 9 are selected as the sensitive words that should not be recognized by the ASR approach. We use all signals that are between 3 to 10.2 seconds long that contains digits after recognized by each target ASR system. So the results training datasets for DeepSpeech 2 contains 750 signals. The validation set contains 413 signals, and testing set contains 371 signals. For ART, the numbers are 6689, 392, and 36. Note that the ground-truth transcription is generated by supplying the noise-free signal to each ASR system. Because we want to ensure that ASR model initially recognize sensitive words. This is why the files counts are different for each ASR system. The graph here shows the experimental results for our proposed self-supervised learning features approach and SDFT-based models. The results of our proposed approach are promising according to both ASR models. Our approach reached higher MR, which greater than 87%, and PR, which higher than 70%, compared to baseline models, which are around 60% MR and PR. The results indicates that self-supervised learning features help produce more distinguishable noise perturbation for sensitive words. So the table here shows the detailed digits distribution for each ASR system. The training datasets for DeepSpeech 2 contains 8472 digits. The validation set contains 476, and testing set has 413 digits. For LRT, the numbers are 7934, 446, and 378. So the table also shows number of sensitive words that were not recognized in test set. For DeepSpeech 2 and LRT, the numbers are showing the table here. Most of the spoken ones and twos are not recognized and successfully being filtered and masked. Other digits, such as 3, has lower manipulation rate and others. Also, we find that there are less samples for higher digits. However, our proposed model still learns well and successfully manipulates many of these digits. So for this paper, our proposed approach generates a specific perturbation and then inject into signal to prevent a white box ASR system for recognizing sensitive words. The approach is robust and has promising results. However, the experiments are limits in certain ways. First, for now, all experiments are conducted in simulated environments. One future direction is to play the noise over a loudspeaker for injection. The proposed defense mechanism in this paper aim to inject a specific perturbation digitally to a given signal, which limits real-world feasibility. Also, universal defense should be studied. Universal defense indicates that a single perturbation can be used on all the signals, while still filtering all desired words. The inference time can be further decreased to make an real-world defense here. So that's it for our work. Thank you for listening and your attention.